Good morning, people. About 5 a.m. here, and I figured I'd start you off with a video this morning. I had someone tell me that this is shear. Now, this is what is known as shear. When I say that, it's the same as me saying that gravity is what you people call something when you just let it go and it falls to the surface where it can't fall any further, which we know is the ground. And then you call, oh, that's gravity. Instead of just thinking about displacement. Displacement is what's going on here. The fluid around you, the air around you, let's just call it air, right? And you have a ball here. If you let go of the ball, this ball weighs more than the air around it. So this air can't displace more than what it weighs. So it sinks. Just like a boat, a ship. Okay, just like a ship on the water, it sinks. So you understand how boats work through displacement. Through displacement, here's a boat, and the beam will now be the water. So let's do our boat like that, right? That's the boathouse. And it has to displace more water than what it weighs. So this is water. I'm going to call that water. This boat has to have a surface that displaces more water than what it weighs. So let's say it weighs 1 ton total. It needs to, as it pushes into the water, if you will, it needs to displace 1 ton of water to balance itself. Equilibrium again. Sometimes that water, and you'll see the water line up here. And that's because, so the boat will sink below the surface. So the boat goes below the surface as you see it, like that. And this is that extra surface area that gets involved, not just the bottom of the boat, but the side walls of the boat then starts displacing. Starts in this displacement thing. All right, so now and as you load more people on it, the boat may sink even deeper. May sink even deeper into the water, displacing more than what it weighs. And you'll see these oil tankers, man, they're down here. They're deep into the water. All right, it gives them stability, too, to be deep in the water like that also. You don't want to just be on the top. You just fall over when a wave comes. Just rotate over. So it displaces more. You don't say gravity did that. For some reason, physics and engineering understands this is displacement. But all of a sudden, when we come to fluid dynamics, the air around you, it's no longer seen. It's invisible. It's invisible. It's not seen. So when this apple falls, it's a green apple, it doesn't stay there because the fluid around it, the air around the apple can't displace more than what it weighs, and the air around, the molecules around it, the air, the gases. Air is a gas, right? It can't do it. Now, air does exist. You know that when you blow up a balloon. It's a tied knot there. Tied knot. Anyway, when you blow up a balloon and you start squeezing it, you'll see the balloon stretch out here in different directions as you displace that air inside there. As you squeeze it, it pushes around out somewhere else. It has to, and you're displacing it with your hand pressure, right? You trapped it. This is not trapped. These air is compressible. It can move out of the way. We don't want to be walking through a solid. We wouldn't go anywhere, would we? If we tried to go through it, walking, we wouldn't be able to walk anywhere. We wouldn't be able to go through the air. Sometimes that air comes at us pretty dense, and that would be like a nice windstorm, and you try to walk through it, and that air is like, whew, coming at you, and you're trying to walk through it. So you're trying to displace this airflow, and it's being replaced by more air behind it. And so, of course, you got drag and everything else. That's a longer video. But this one is now, we're looking at this beam. This beam is being loaded here. Interesting, the narrative of this is from a university, and they state that they're using deflection. 4-point bending, they state. They never stated they're shearing this product. And I'll show you more clarity on shearing in a second, but they never said they're shearing it. They said they're putting it in 4-point bending. 4-point bending. Now, interesting, when you're doing testing bolts and all that, you put them in a shear test, if you will. And it doesn't say, well, we're going to subject the shear test involves 4-point bending. But when we get to this, now we're back to that gravity thing. You can't understand it. Well, the ship's not going down because of gravity, it's displacement, and they understand it's displacement. They don't have a, they don't say, oh, it's gravity. It's a displacement issue. But when you come here, it's no longer you actually say 4-point bending, right? But then when you see the crack, you say, oh, that's a shear crack. Wait a minute, you just said you put it in the bending, and now you're telling me a shear crack developed. All right, tell me how. You just told me the stress you applied was a bending action, and yet you're going to say your test now is a shear test. It's not logical. I don't care what people think about what you're taught and trained. Oh, it's a shear crack. Yeah, it's close to the supports. Shear crack. It's close to the support. It's not at the support. Now, I usually take my time and do long reveals, like my bucket video. I took 5 years, I think it was. Was it 3 years? 3 or 5 years to finally reveal I was just exposing all the idiots that would steal your data, steal your stuff, and do duplicate videos. And now this one, I'm not waiting that long, but I want you to see right here. This is a fine crack. I'll go next to the crack, and the crack's on the other side. There's the crack here. It's a very fine crack. That's the beginning of the fracture from here, the failure from there. It's a very fine crack. And I'll do it for you guys. But here's the steel. Right there, see the steel? So I'm going to run the steel down the bottom of there. There it is, crossing the bottom of the crack. That's the bottom of the crack right there. That's the bottom of crack, which is on top of steel. It's on the top of the steel. Here's the steel here. Top of steel. The cover, this is the cover, the lower part below the steel. The concrete cover. At this point, there's no development of the crack below it. No development that I can tell of, right? And then the crack stops here. All right, so it stops there. This is so from here to here, this now becomes your tension. Crack. It's tension. It's opened up. Tension created it. And from here, this is your neutral axis. Okay. And this is your compression zone. This still has... Hey, George. Cat. This is your compression zone. So that looked like that when I wrote it, guys. Sorry, I do shorthand sometimes my own. This is compression zone. So zone, and there's a C. But all together, it's, yeah, I'll do something like that. Even though it looks like a G, I know what I'm doing here. So I'll do that. And it's my own version of shorthand. I just want to show you what I do sometimes. So don't think I'm making a mistake all the time. Sometimes I get mixed up that you guys are looking at what I'm writing. So this becomes the compression zone. At this point, just at this stage, if we can freeze it in time and not, which we're doing here, and not going forward any longer, Now, Charles, you wrote me. Charles is an engineer, and we're talking about cracked windshield, and his windshield's getting larger and crack. A cracked windshield. Okay, so this will be a cracked windshield here, what we're looking at. So bear with me. I'll clean this up in a minute, the screen. A cracked windshield, or as you guys say in Europe, windscreen. All right, so here's a cracked windshield here. Here's a windshield. And here's your fine crack. Well, what's left, what's beyond the crack, let me do this one. Here's your windscreen now. Your windscreen if you're in Europe, or windshield here. So I'm now going to add a crack. Let's do it again. I'm going to add this crack here. Oh, okay, just like this one in the beam. I'm at a crack there. So what you're looking at is the what's left, the balance of what can take on the stresses. And that's his windshield right here. This is the rest of the glass. So it looks like that. This is not going to take on any stresses because it's cracked. There's nothing that's going to bridge across it. There's no air reinforcement there. So what's left is what's left. It's this section, and it goes up here. You know, it's above it. It's around it, but this section here is all I care about. This there. As you ride down the road, the stresses that the windscreen will take, flexing and moving around, it can only go in the way you see the yellow. Everything else, but you see the blue also, but not in that red. And so the new stress, the bounce in the road goes, it's like now there. Now that it's reduced again. That's that new crack. You can go any direction you want based on the stresses. And then it takes another bump, and you get your fractures again. Now it's left. So you see the pattern of it there. Only thing that's left is everything around it. That's it. You take your next bump. The next bump in the road pushes the crack all the way up to there. Now you've got, in essence, two windshields. You've got this side, a section. You've got this section. You've got two there. The fine crack is still there. It's not waterproof. It's fractured. All right. So this is the same as what you're looking at here. The stresses were applied, and what's left, here's that crack. This cover, not to be confused, this cover here is just a cover over from the rebar here. Taking a little liberty, it's gave us a larger cover down here. So just like the windshield, here's your crack. All right, from the rebar, that's equivalent to the bottom of the windshield. And this is all that's left. All that's left is the outside of the windshield here. All right, this is what's left. And as you keep applying loads down, deflection down, what's going to happen? The crack will develop even larger. It will continue until it's fully fractured. Upon fully fracturing, at the same time, the stresses are being taken on by the rebar. If we can, I've shown you this in real life, a piece of routed out where rebar is in the concrete. This is the top view, I think we're going to go with. I want you to think about like we just was able to cut this right here. And, okay, I know what to do. So here's the concrete section here that I'm going to do this one. I'm going to do this one over here like this. And on the other side, I'm going to put this side, the loading side. This is this one. And so as this deflects and goes down, deflecting down. Remember, that creates a bit of a rotation. This fracture is developing up. This one here is developing up. And remember, right there is at that point, that's your neutral axis where it transitions over from the fracture open side, the tension side, as it's mostly known as, with the compression side. That's the material that's left behind. Ultimately, as this deflects down, it just changes the scale. Now it's smaller, and now it's smaller, just like the windshield. As you keep applying the load, it's going to resolve itself, chasing itself up. That thing was small at one point. That little fracture counts. But it's above the steel. So your steel down at the bottom is getting loaded, and it's deflecting, and it's being put in tension, well, for the most part, because it also has a neutral axis where it transitions from tension to pretty much no tension. It's just a rotation, and that is resolved right there, literally right here, where the first crack starts developing. That's its neutral axis of the rotation of this going down, and this section not being able to go down, met by the when it's trying to resolve itself there. Part of it so Newton's third law is defective in that it says equal and opposite. It's not opposite, all right? It's equal, but it's not opposite. It's not just opposite. If it was opposite, so Newton said gravity, and Newton said equal and opposite. But I enjoy Newton's stuff, but it's so simple. It cannot be equal and opposite. If it's equal and opposite, that means when the wind blows north, there would be an opposite, a south blowing wind that would cancel it out. That would be equal and opposite. But it can be just equal and opposing, or equal and balanced, equilibrium. It's a balance that's going on. So if you're going to push air at 10 miles an hour this way, the air will move out of the way. It's resisted to some compression, so it moves out of the way, and then it just gets pushed around. Air rotation, all that. It's all in equilibrium is what I'm driving at. Not creating new energy of that nature, but energy is created. And I'll get to that in another video about, you can't create energy. And I know I troll people when I say you can't create energy. I'm just being smart, because clearly the sun creates energy. It grows plants. The sun does. Without the sun, the plants don't grow, right? Wintertime, it goes dormant. When the sun comes out, that sun is creating energy that is making the plants grow. And so you're not creating new energy. Well, isn't it kind of when the Earth tilts on its axis, and then there was no life there, and then all of a sudden life appears? Isn't that creating energy, creating all types of things, a growth, a demand, this new energy, this new creature, this new living thing that the grass blade wants to consume. And so, I guess I'm digressing a bit, but this is how deep I go. And I have to come back to Newton, right? And I like putting a K in front of his name. Newton. So the forces here are not just what you think, that it's just shear. No, there's a neutral axis here at one point. And that's where the rotation starts to begin, right there. And then, so that's your first crack. And as this stresses down, the next crack, the next one. At some point, this becomes, nothing. It can just abruptly fracture that last section off, no big deal. And then all the stresses are still in the top of this rebar, bonded to the top of the rebar, of the concrete. As this deflects down, it's an explosive release. Kinetic energy is released explosively, and this rotates into the air. As I tell you, this is a rotating force, and you'll see this eject up, actually hit this device here, and then bounce off. A elastic collision, elastic collision takes place. But this is called shear stupidity, is what I state. It's not shear. It's a result of deflection. And it's just simply your fracture develops, and then what's left is the neutral axis changes, and then it changes again, it changes again. Just because you can't see it change to you and I, if you will, in this image, it looks like it's just all at once. But it didn't slow down enough. But to get from A to B, there was a transfer. Okay, now the neutral axis is here. And then next, now the neutral axis is there. And then here. And as I freeze frame this, we see it's here. We see that it's here. And down there is where the initial crack was. And this is doing nothing anymore. It's separate. What's left is this doing the work, and the top of the reinforcement as it bridges across down here. And if you can't see it from here, I'm sort of in trouble trying to explain it to you, but let's go from here. So let's see if I can get this frame to catch it for you. Get one more. I've got to slow down. I've got to slow down. Take it, let me get a second. Let me take my liberty. Okay. Trying to get one more crack. Alright. So we'll just go with that. So here we have, so there was that neutral axis. And now the shift, so here would be the continuation, right? But the shift happened because this is, remember that I said I showed you this windscreen. The windscreen. So there's our neutral axis before we developed more. And there's our neutral axis. I said it was there and there. And from here, the direction goes this way. Oh, look at that. The direction goes that way. Huh. Interesting. So, you know the way I present. There's the rebar, the reinforcement there. It's already separating. Now, let's go to the path to the left. And you see now there's the axis. Now it's got to be taken up by the rebar. That's the connection of this here. And then again, and then again. But this thing is applying a load still. So at one point it's like, I got the last remaining part. The remainder balance might, let's say, take, let's just use something like 500 pounds of force to break it free. This has got so much kinetic energy in it. Maybe it's got, 2,800 pounds of force at this point. When this gets to this point, it says, snaps off. Flips, this rotates down, flexes down, because it's steel. Remember, steel's inside there. So it flexes, right there, there's our point. There's our rebar. Sorry for going up there on that one. And I'm taking exaggeration. Here's our point here. Let me change colors on that for you. This point here would be here. And so there's your rotation because it applied loads here. And you'll see this eject up and release. I'm going to play the video now. I'll let you look at that for a second. So remember, this is changing, right? As the crack stops here. Now it's changing. It's going to develop down there. This one's done. This is done. So it's already through. It's separated. This is not playing along anymore. Only thing that's playing along is this rebar at this point. This is complete. It's done. It's finished its task of resisting. This is finished its task. This is done. This is all the way through. This is completed task, right? It's completed task. Now we're just working this, and we're going to get to that explosive moment there, and you'll get your rotation and your ejection over towards this device, and there it is, there and there. Now let's show it. And there's the rest of it. So here's your where it was, and as I told you that, and there's your rebar right here. I'll move that away now. So there's your rebar at top of it. And this is the part that broke apart. As you can see, the rebar is in place here. So this is all that you're looking at, is the neutral axis changing over multiple places. And there's your direction there that way, and there's the reversal of it, and this direction. So you can see so there was a neutral axis there. There's a change of direction, and there we go there. Put a plane there. There's the rebar, right? So rebar and neutral axis. Whoops. So on this side was the fractured side as it was going this direction, right here. As it was going this direction. And then the balance just left was the same as this going up. When it stopped there. And then this one stopped. When it stopped there and it was there, it started developing to the left, to the west and east of this image. It started developing this way and this way. And this one completed its task. Remember, completed task. This one, all it was left was the rebar over on this side, and all these forces were resolved by. It was still going down, trying to stop itself. Here, now I don't discount its connection that it was at here. That gave it a sort of a pinned location. Yes, it's on a roller, but I think it's a roller connection ultimately down here. But that gave it a little bit. That's another video that I was making on that subject too, about these connections that they're doing. Oh no, I already made that one. I made one of them. So we get our change, our neutral axis here. We get our change of directions again, and so change of direction, and you can see it now. So these are our neutral axis points where we change directions. Forces were only resolved here in the rebar this direction. Once it's split out here, that was done. It's completed task, only being able to resolve itself down here in steel. So if you would observe this somehow, to be able to observe this fracture and like this, and the beam was still in place, you can bet this is what's going place. This is what's taking place. Like the cracked windshield, it's moving down the line. At some point, this being, say, 2,500 pounds of force or 2,500 pounds of force, and this only needing 500 pounds to complete that last section, you get your explosive break and rotation. Let's look at that crack. I want you to pause it if you like, and I'm going to show you it develop now. There it goes. There's the ejection. This is ejecting it off. See this here? Let's say that's 2 inches. And look down here. Let's call that 1/4 inch. So you can see that this force, remember I said like this goes like that? I did the drawing down there like that and said this is where it's taking place. Well, there you go. There's the break in the underside, the cover now. And let me clear that up. And there's your break in your cover. Right there. See the fracture? And that's the rebar again, taking some stresses. Let's get rid of that. But there is your break of the cover, and that steel now is being able to quickly release. It's no longer trapped by the cover holding it. The cover was holding it. It releases also. It releases what it could hold. In the bottom, it was acting as a strong back, an upside down strong back. The cover was now playing along. When it releases, when it pops free, it allows the rebar to bend. And then basically you have a baseball bat. There's a baseball bat. From the forces here, point here, this is the hand holding the bat, this whole section here. Swings, the batter swings. Kinetic energy. And whoop, it ejects this section off here. Into the air. Let's watch the rotation. She's free now. Now it's just a matter of flight. It's just air time. But look at the crack again. Observe the crack. Observe the distance here is larger, much larger there than here. So you got rotational inertia. Rotational inertia going on. And this is the baseball bat deal. And let's watch it go. Into the air. Notice how it's not sliding across this concrete. Notice how this nice, beautiful debris stands up here. The energy shows that this is going down so much faster than this. We see some breaking of debris, but we don't see the return the same like this in equilibrium, equal but opposite. We don't see that observed exactly there. We see the fracturing of the material separating from here. We see some air time one like that one there. Small air time. This breaking. There's the debris ejecting down. That's that break I told you about. This is a part. There are parts upon the rebar. They're still bending down. Remember, they're released. So what does this tell you? It tells you that the equal and opposite. Let's do this again. This one. And then let's do this one as the opposing. And then let's do that. Here's our neutral axis, right? Our forms. And then this one also runs into the one to the right, also runs into where it did its sharing. Remember, now it looks like it's fully through. Remember, it had energy built up in it also. As it was deflection, even though after it broke, this side released because this participated to pin it, if you will, lock it in place. And it wasn't for free that it was locking it in place. When this came down and when we finally get the release of this, that energy is also released over here. And the rebar, they're about balanced with this one. So you see the symmetry now in your cracks. And the new one developed. This was an easy one, and also on the right side of it, you can see the energy up in the air. Now I'll show you what shear looks like at this point. Little teeny shear right there, backing out. There's your bypass, your true shear, if you will, right underneath of this rebar. Here's the rebar here, if you can see it right there in that little window. I'm going to remove the window, and now you can see the section of concrete that's going to break off. Well, it's already broken off, and there's a little teeny bit there. But let's let this play, and you now see how it's equal and opposite. My man, right? It's just equal and balanced. All right, let's go with finish off the flying. You see the rotation, its path now. I mean, you can't deny its path. The next one will be, you know, there, and then there, and then you can follow it. But ultimately, it's just doing this. Now look at it rebound. I guess they let go of the loading device. I know they do. Just follow the path of the specs, and they'll tell you. Well, obviously you can see the path of this, but that shows you that kinetic energy. And this is the baseball bat right there. This piece of steel is the baseball bat, ejecting it in the air. Jeez. Look at that. Shoo. And here it comes, impact. And there's your steel here. If you can see it.
Now remember,
that's your steel.
This is a beam in which we have left out the shear reinforcement.
It says no shear reinforcement. But I'm stating that this is not, this is just what I stated.
This is the consequence.
What's up, Georgie? Alright, so they released the load on there, so that's why you get the rebound. I remember seeing the gauges go back to 0. But there's your reinforcement, as you can see it there. Neutral axis, duplication, rebar, rebar. So when finally if the strong back fails, if you will, the cover participating allows that abrupt change of loading. Oh, that's what it was. I think I wanted to just let you see it twice.
If we slow down
there, okay, so there we go. So the guy's talking, so we'll let him talk. But again, now we've already developed that.
Here is that failure again.
And it goes 2 directions.
Look how sudden it is.
Okay. Bear with me.
That failure
I'm trying to catch something.
Again.
Okay. So you see it again. There it is, complete there, but you still got loading going on. So remember, the change of direction is going to happen now, or the behaviors. There's the fracture developing right there. Strong back's failure, the rebar, and we're going to get change of directions. So now this rebar is going to take it. It's taking the load, the stresses, with the reinforcement still bonded to the bottom half of this. There we go. I know what to do. The strong back being the bottom half of this concrete. Okay. And as this rebar deflects down, it stresses here. And you get this break here. And there we go. At that deflective moment, if you will, this deflection here, so let's put the rebar in. Yeah. So let's put the rebar in. You can see the rebar is no longer straight. So it's not for free. There's your rotation. This is also your neutral axis point. It's your change of directions. So, and that rebar bending has a lot. It has that grip and, you know, the profile in it. It's not for free. It's got the profile. It just doesn't act the way that you just want it to. It's also bending and stretching. And now when it stretches, the concrete can't stay bonded to it. So the concrete can't stay bonded to this concrete now, to the rebar. And I guess I'll go inside the voids. It can't stay bonded to it as it stretches. And once it does that, it releases itself from the rebar right over to where it can, and before it resolves itself going way out here and ultimate failure happens. Let's let it go now. See, now there you go. Now change directions from here, and then it took this path, the crack windshield path. And it's still going down, as you can see. The abrupt release from here created this height of the particles, the dust off the top, if you will, that you normally wouldn't see. But this created the abrupt release, and there you can see the particles as I stated. This was the release. This was the release here also, all abruptly. You remember that, say this is putting out 2,500 pounds rather, and this only needs 500 to release it. And there's the baseball bat. Boom. Times 1, times 2. Section 1, section 2. And each one has its own story to tell, including every bit of this crack. This crack. Back up just a touch. And let's let it go again.
Here is that failure again.
Okay, there we go. You see the development of it. So release, and it's right about here. And as I go forward a little more, then you'll see you'll go here, and then it takes on the new moment of this direction to complete the windshield crack. Okay, so I should have went further. I should have went straight up. Oops. So what's amazing is that if you search, just search, tell you guys to search, you'll find that bolt shear strength. Okay, so shear. Looks like that. Okay. I call this, wait a minute, forget that one. Go here, removing studs, old timers tricks, shear. Looks like that. Shear. Looking like that. This is shear. Looks like that. The Rider Project. Okay, this is shear, double shear, single shear type stuff. Shear. It all looks like that. A bypass is going on. Shear. If we look at his video, he makes it clear that he states it's a bending one. I'll end that with that. Hold on. So this one, the video here, we'll click on that right now. And listen to it. It says 4-point bending. Material Labs Online. Oh, I'm going to have to change the speed. Hold on. Okay, here we go.
This video shows a reinforced concrete beam containing no shear links being tested in bending. Specimen is made from concrete containing regular Portland cement.
Being tested in bending, his own statement. So it's interesting how the brain works, right? The brain, you said it's being tested in bending, and then you said, oh, we got shear. And yet every other testing and test for shear says it's a shear test. It doesn't say it's being tested in stretching. When you've got that double shear action going on, and here's a plate here, and you run a bolt through it. Oh, we're not testing this in tension. It's a shear test. It's a shear test. And this guy makes it clear. I guess this is your brain saying, you know what? I know what I'm looking at. This is bending. But yet, all engineers are told this is shear, so I'm going to say two conflicting statements. Yeah, they could exist together if it really was bending, and it was so bending. All right, they can't exist, all right? You can't have bending and then say your result was a result of shear. It was a result of you loading it bending, as you stated. Listen to it. Professor Tin Eibel, not to be confused with
This
Tin Bell.
video shows a reinforced concrete beam containing no shear links being tested in bending. The specimen is made from concrete containing regular Portland cement.
Tested in
The
bending.
rebar is regular reinforcing steel. The loading diagram shows the beam being subject to 4-point bending.
The loading diagram shows he's subject to 4-point bending. He doesn't even say subject to shear. He says it's subject to 4-point bending. All right, his own words. Professor. 4-point bending. Right, there the arrows there. There's your 4 points. 1, 2, 3, 4. 4 points. And I guess your amygdala, you'll probably get upset if I don't put a decimal on it or circle them. All right, so 4-point bending. Agreed. There's just to say that's the steel at the bottom. And he's bending it. And we now know that would be there. And that resolved itself like that. We didn't see it on the right side. Interesting how this works is that both of them probably getting the equal amount of stress. But the materials, the concrete material and all placement, it's random based on your placement. It's a reason behind why this side is the weaker side to gave first. This side obviously was just superior it could be by practically, nothing at all. Maybe this takes 500 pounds to get that bursting, and this is 750. So it was very close, except for this one is going to go first. Now, if you see some cracks develop here and then some over here, maybe these numbers are closer than you think. And when this goes first, this still was the lower one compared to this one. All right, if they go together, then it's pretty balanced. If you get mirrored cracks, your reinforcement and your concrete is pretty balanced. 4-point bending.
The specimen is made from concrete containing regular Portland cement. The rebar is regular reinforcing steel. The loading diagram shows the beam being subject to 4-point bending.
Yeah. His own words, not mine.
The testing rig is now starting to apply vertical loads to the specimen,
2 meters,
and the beam
2
starts
gauges
to
above.
deflect. Then quite suddenly, we have an explosive failure near a support.
Explosive
This
failure.
is what we call a shear failure, and it is something that...
He said explosive failure, we call it a shear failure. Well, any other would call it a brittle failure, a brittle fracture. He could have explosive. It's interesting, it's crazy how this guy's a professor and nobody's questioning it. Like my gravity thing, nobody, tons of people questioning gravity now. But I'll say I'm one of the first people that shot it down besides Einstein. And I shot it down before knowing Einstein was shooting it down. And it just never made sense to me. As a child, it didn't make sense to me. Later, I was able to research that, Newton didn't quite prove gravity. He said he couldn't prove it. And then I found later on again, following up, that, Einstein didn't prove it. My whole problem is with the gravitational pull of the moon, they tell you, and the data we have, such as astronauts landing on the moon, and they're able to they have to use gravity boots to walk around. I'm like, whoa, dude, you're messing me up here. You said that the gravitational pull of the moon is so great that it can lift only seawater up, not lakes. But yet a guy can land on the moon. I'm being facetious. Guy can land on the moon, right? And he needs gravity boots to keep himself on the moon. So they say, well, it's proportional to his size. I'm like, well, he's right on the moon too. Proportional to your size is when we're on planet Earth. Now you come 25,000 miles, whatever, 2,200, whatever it is, 250 miles closer. You're on the source of this gravitational pull. I'd say that's pretty damn proportional. You changed a lot of damn size for a human now that close at the source. And he still needs gravity boots to walk around? Or he's bumping around in the air, jumping around like he's in free space. No atmosphere. So I'm like, I doubt this whole thing. As soon as I saw the guy bouncing around in space, that's when the first time I saw that video, I'm like, well, that can't be from that. My brain just quickly put it together. Remember the process of the amygdala. It said, huh, no, that data, this is conflicting data. It says those don't work together. You can't have, say it's the moon. I got 2 files now. Moon, gravity, size related, everything that says why gravity's okay. Apple, and then, which I didn't believe the apple either. But then the guy's on the moon, and now he can't keep his ass on the moon. He's got to use some weights to keep him flying off the moon. I'm like, no. Let's debunk themselves. That'd be like me telling you guys, look, the moon is what's lifting, is the gravitational pull. And my reason is why it doesn't lift you up is because it's proportional to the size. So the bigger you are, it works. And you somehow bedazzle because I convince you that the ocean is acting as one big mass and not an individual surface. It's acting as one large mass. And I tell you, look, proof of this is when every time you see the moon at X and the sun at X, we get high tides. And you're like, oh, okay, yeah, correlation, equals causation. So you're like, gravity. It's moon, it's pulling it up. It's going away towards the moon, high tide. So that's a pulling action. That's the apple falling. So it's equivalent to a pulling action, so it's gravity. Even though it's going away from the earth, up here, not down, towards the earth, the ocean, the one that's doing it is the closest thing I can find. It's got to be the moon, because every time the moon comes around, this happens. Correlation equals causation. You hear a loud bang. You look out the window and you see a guy lying on the ground. Well, it appears to be dead as fuck. You say, oh shit, somebody shot the dude. Upon further looking, you see, oh, it was a roofer. And you look up and you see the other roofers on the roof. And you see that, oh, dude fell off the roof. What was the loud bang, you wonder? They're not the same. They're not related, though, are they? Okay, ending the video. In a future video, I guess I'll do this. In a future video, I'll go over the one that has stirrups in it and how your fractures develop. Remember, just don't look at this like that. Think of it as the neutral axis, what's left of the windshield. And you can profile it. You can profile what's left of the windshield like that. This is what's taking on the loads. The crack is no longer taking on the loads. In this case, though, the exception is it can bridge the crack because of steel stirrups. Because of steel, it can bridge the cracks. Nevertheless, even though it's bridging, we still have the windshield effect going on of how this is working. And in the bottom part of this section, it's going to be a much deeper video dive for you. I don't know when I'm going to get to that. But this is now the steel being stretched. And you see all the opening. You add all that up and you can determine what's going on here. You could also measure from here to here and say you have 112 exact inches. But when you started off, you had 110 exact inches when it was flat. So you can see your rotation is taking up 2 inches. I'm going to get deeper into that, but look at that. That's rotation. That was 100. This might now be 109 inches and 7/8. It's a little bit more compressed at the top because of the rotation. Is that possible to get 107? Wait a minute, what I do? Well, 109. I want you to think about that. 109 and 7/8. Is that possible to do that? Well, I need a benchmark, a point in space I'm measuring from. All right, take care. Well, you tell me. I'm sorry, you tell me. Bye.